Okay, so sometimes you might be faced with an integral that we don't know how to do. For example, now let me write down the usual preamble here. Co-16B. Today is February 22nd. Not the pen I should be using. Cool. So sometimes you might be facing an integral you don't know how to do. Well, I mean, that's often the case. We don't know how to do it to start off with, but we actually don't have a method for doing. So here's an example. Something like the integral of the square root of x squared plus 16 dx. There is no method for us to do this. There are methods to do this in 21B that we're not going to talk about. But right, if you try to do this, you're like, well, the only real seemingly plausible choice here would be to let u equal maybe like x squared plus 16, but that doesn't really work out. So when you encounter something like this, you might be encouraged to use a table where you look up a formula that has that specific format. If you look in the tables, this is formula. So I don't have the table for me. I have the formula. So formula number, which one is it? Number 21, which is on page 418, says that the integral of the square root of u squared plus or minus a squared. When you look at formulas like this, you should always think of u as the variable and a as a constant. B is also a constant. Is equal to 1/2 parentheses u times the square root of u squared plus or minus a squared. Sorry, plus or minus, oh man, didn't know that's right. And then plus or minus a squared times natural log of the absolute value of u plus or minus the square root of u squared plus or minus a squared. Holy smokes. It's a lot of terribleness. Plus c. So then after we look at this formula here, it's our job to then identify in our actual expression what is playing the role of u and what is playing the role of a. In our function, u is being played by x and a is being played by 4. And we have a plus, not a minus. So we would say that the integral of, and I would probably write it as x squared plus, sorry, the square root of x squared plus 4 squared dx is equal to, and then we're literally just tossing x in for every u and 4 in for every a. So we're going to get 1/2 times parentheses x times the square root of x squared plus 4 squared plus 4 squared times the natural log of x plus the square root of x squared plus 4 squared. Let's see. On the other hand, let's do another one because I think it's worthwhile here. If we were asked something like to find the integral of the square root of 9x squared minus 25, the same formula is applicable, but now my u would be 3x, so that u squared is 9x squared, and my a would be 5, so that a squared is 25. And I'm going to be using the minus instead of the plus. So here, this integral is going to end up equaling still a 1/2 times my u, which is now 3x times the square root of u squared minus a squared. So it's going to be 9x squared minus 25 minus a squared times the natural log of the absolute value of my u, which is 3x minus the square root of u squared minus a squared. So the idea is to look at your integral, try to find the formula in the book or what in the handout that it is best fit by it, and then figure out what you need to make a and u and maybe b equal to actually do that. In my opinion, they're not the most interesting questions because it's kind of just like a hide and seek game, for lack of a better expression. Let's look at one more example that uses this formula, just to kind of see how you might get something that doesn't look like this from the jump, but it still requires this formula. Let's say we wanted to find, sure, the integral of the square root of x squared. Yeah, x squared plus, sure, 6x. So at first blush, it does not look like this formula should apply, right? I don't have the square root of u squared plus or minus something squared. Certainly not plus or minus some constant squared, right? Sure, 6x is something squared. It's the square root of 6x squared, but square root of 6x is not a constant. So you're like, oh, so here's what we have to do here, which is kind of, oh, I forgot my dx, which is maybe kind of not very intuitive. We're going to complete the square. So we're going to take our x squared plus 6x in the square root. And what do I need to add on here? I know maybe it's been a while since you've completed the square. What do we need to add on to complete the square? Oh, good question. You guys are like, do you guys remember, did you, just honestly, do you remember how to complete the square? It's okay if you don't. You can say no. So the way we complete the square is you take the coefficient of x. So if you got x squared plus something times x, so let's use a whole new page for this, just for 1 second. So completing the square. If you had like say x squared minus 10x, and I wanted to complete the square, what I would do is I would take my negative 10, I would divide it by 2, and then I would square it. And that's going to be negative 5 squared, which is positive 25. So I would rewrite x squared minus 10x as x squared minus 10x plus 25 minus 25. So I'm not changing anything. And then the x squared minus 10x plus 25, that part where I added the 25 on there, that now is a completed square. What do I mean when I say it's a completed square? I mean that I can literally write x squared minus 10x plus 25 as some quantity squared. X squared minus 10x plus 25 factors as x minus 5 times x minus 5, which is x minus 5 squared. So this is equal to x minus 5 squared minus 25. We have completed the square. So same deal up here. We look back at this example we're doing here. What I'm going to do here is I'm going to take that 6, I'm going to divide it by 2, which is 3, and I'm going to square it, and 3 squared is 9. I'm going to add 9, but I can't just add 9, otherwise I'm changing the expression. I'm also going to subtract 9. And now we can rewrite this as the integral of the square root of the x squared plus 6x plus 9 becomes x plus 3 times x plus 3, or x plus 3 squared. And the minus 9 is minus 3 squared. And now this looks very much in the format of formula number 21, where our u would be x plus 3 and our a would be 3. Right? Because we've got x plus 3 squared minus 3 squared. And then we're just going to throw it all into this gross formula over here. It's really kind of not fun. In case you couldn't tell, I'm not a huge fan of this. But it is worthwhile in that sometimes we actually do encounter things that are really, really hard to integrate, and it's easier to look it up on the table. Just like way back when before they had really nice calculators and you had to find like natural log of 3, you would look it up in a table because there were literal logarithmic tables and trigonometric function table, right? I know what a time there was when you had to actually go look up like what's tangent of 32 degrees. Let's go look at the table and find out. I know it's kind of, I mean, I never had, I'm not that old, but people had to do that once upon a time. It's kind of weird. This is going to be equal to, let's see, 1/2 times my u, which is x plus 3, times the square root of, now let's be smart here for a second. Instead of writing x plus 3 squared minus 3 squared, I could just write x squared plus 6x, because they're the same, right? X plus 3 squared is x squared plus 6x plus 9, minus 9 is x squared plus 6x. So I could write this as x squared plus 6x, or I could write it as x plus 3 squared minus 3 squared, if you want to do more writing. But it would be just as good to write this part as x squared plus 6x. They're literally the same. And then it's going to be a minus because I have a minus there. So it's going to be minus a squared times the natural log of u minus the square root of u squared minus 3 squared plus c. That's it. I would argue the hard part of these problems usually is figuring out which formula you're supposed to be using. Which we are not really experiencing with these examples I'm giving you. Well, let's look at another example. Is that another example? Yeah, so let's look at this next example. Let's say we want to find the integral of, sure, x over, I'm going to change this up just a little bit, square root of, no, I'm not, x to the fourth plus 2x squared plus 2 dx. Blech. So what I would point out here, well, let's give ourselves a little more like it. Let's say they gave you this problem and they told you which formula to use, and we know we want to use the formula that the integral of 1 over the square root of u squared plus or minus a squared du is equal to the natural log of the absolute value of u plus the square root of u squared plus or minus a squared. Let's see. We know we want to use this formula. To use this formula, we have to make our integral look like that. So I need something squared plus something squared. If you see something that doesn't look like x squared plus something squared, or some quantity squared plus a constant squared, that often means it's going to require us to complete the square, like we did previously, which is nobody's favorite, but we'll do it anyway. I mean, okay, math is not everyone's favorite, but we do it anyway, right? It's my favorite. It might not be your favorite. So let's complete the square here. And the way we're going to do that is we're going to see that we can write this as x over the square root of, I'm going to have x to the fourth plus 2x squared. And so I'm treating this as like x squared squared plus 2x squared. X squared is kind of like my thing here, my x in the previous problem. And then to complete the square, I'm going to take the coefficient 2. 2 divided by 2 is 1. 1 squared is still 1. So I'm going to add on a 1. And now watch this. Instead of saying add 1, subtract 1, and then add 2, let's just make it work by saying, well, if I want a plus 1 there, I still need another plus 1 to make those the same as they were before. You could also write minus 1 plus 2, but that is literally the same as just plus 1. And then we're going to factor the thing that we just completed the square for. All right, this is x over the square root of the quantity x squared plus 1 squared plus 1 dx. What's kind of funny here is now we're actually going to do a u sub to make this problem look like what we want it to look like. So we're kind of doing the u sub and also making the choice for u at the same time. So we're going to let u equal x squared plus 1. The thing that's being squared right there. Just like, hey, look, over there in the formula, that first part is being squared. So u squared is x squared plus 1 squared. So it makes sense to choose u equal to x squared plus 1. And then our du is going to be 2x dx. I have an x dx, so I'm going to multiply both sides by 1/2 here to get 1/2 du equal to x dx. Great, I'm on my way. So x dx, that's equal to 1/2 du. X squared plus 1, that's equal to u. So now I can rewrite this as the integral of 1/2 du on top, or 1/2 on top and the du out to the side, over the square root of u squared plus 1. And now we can pretty much apply the formula. You might, if you really, really want to, rewrite this as 1/2 times the integral of 1 over the square root of u squared plus 1, or plus 1 squared if you like. But then it's pretty straightforward. Our u is u and our a is 1. This is going to equal, I'm just looking at the formula, the natural log of the absolute value of my u plus the square root of u squared plus 1 squared. But then I should actually plug back in what my choice for u was. That's going to be the natural log of the absolute value of x squared plus 1 plus the square root of x squared plus 1 squared plus 1. Let's see. Just like with a normal u sub, right? Whenever you do a normal u substitution, you then do the integral, and then at the end of the story, you plug back in whatever u was equal to start to end with the same variable you started with. Yeah, of course. Sorry. You should just yell at me, please. Be like, James, I can't see it. Yeah, something. Yeah, we'll do one more. One more, and then we'll move on. Because again, most of this is just like pattern recognition. You have to look at what, or messing with what you've got until it looks like something that you want. Let's do one more, and then we will move along to partial fractions. Unless there's other things we want. I think partial. Someone, sorry, and I keep forgetting. Someone had asked a question about present value, and I have forgotten to like do anything about that. So I don't remember what the formula for present value. Has he talked about present value in class? It's okay if the answer is no. Like it's like some formula for like if you are. I forget. It's honestly something about like if you want to have so much money. It's about like investing. It's terrible. It's something like. It's like if you win the lottery and you get paid out over a bunch of time, they're like, it's kind of like how they say, like, when you win the lottery, right? You could either take like your payment in over 30 years, right? If you won like $100 million, you could get paid out over 30 years, or you could take all the money up front, but it's not all the money, right? Because it's the money you would need to then invest it over those years to then pay out over that time to have the 300 million over at the end. So like if you won $300 million, how nice, over 30 years, that means they'd be paying you $10 million a year, right? No. Yeah, 10 million, right? 10 million times 30? Yeah. 10 million times 3 is 30 million. 10 million times 30 is 30 million. So you either get $10 million a year for 30 years, or they can give you the lump sum of like $160 million at the beginning. And then you could have the job of investing that money so that it earns enough interest so that you can pay yourself the $10 million every year and then still have enough to keep earning interest to keep paying you that. So that's kind of the idea there. The present value is how much money you would need to pay out some amount over some amount of time. And then I could not begin to tell you what the calculation is. I know it's some integral of some weird thing. Literally, I would look up the formula in the textbook. Be like, oh, we do this. And I guess I'll try to have an example of that next time because I keep forgetting about it. But if someone either on Zoom, if someone on Zoom, I think one person on Zoom, has a present value example they'd like to look up or ask me, I'm happy to address it. That said, back to the thing I was talking about. Let's say we had, I keep losing my place here, one second. Let's say we want to find the integral of, let's make it slightly more interesting. Let's say we have x squared times the square root of x to the 6th minus, sure, 25. Oof, this does not look nice. I might be thinking, so again, I think all these problems come with the context of, we know we need to use a formula, right? If someone just threw this integral at me and said, do something, maybe use a formula in the book, or maybe do u sub, or maybe do integration parts, or maybe do one of the other methods I wouldn't necessarily know that I had to go look up a formula or do a thing to get to a formula. But knowing that I have to use a formula here means I know I'm probably looking to look for, I really want something like the square root of u squared minus a squared. That's a typical thing to see in these formulas. To make that happen, I need to choose x to the sixth to be my u squared, which is going to inform how I'm going to make a u substitution. So I'm going to choose x to the sixth to be equal to u squared. And then I'm going to take the square root of both sides to find what my u sub should actually be. This is going to give me the square root of x to the sixth is going to be x to the third. So there is my u sub. Great, let's do, also, that's a really, I also know that's an excellent choice for a u sub, because what's the derivative of x cubed? 3x squared. Oh, look, I have an x squared. That's a really good sign that I'm doing the right thing. So let's do it. So we choose u equal to x cubed. Our du is 3x squared dx. 1/3 du is equal to x squared dx. And then we're going to rewrite our integral as the integral of, so the x squared times dx gets to be the 1/3 du. And the square root of x to the 6 minus 25 is going to be the square root of x cubed squared, or u squared minus 25. Are there questions about that before we move on to the rest of the problem? Not hearing any questions. We move on. I'll point out this is the same formula we used in the first couple problems. This is our formula number 21, which says terrible. The integral of the square root of u squared minus a squared is 1/2 u, or it's all that stuff. So here, u is just u and a is just 5, and it's a minus. So we're going to get, now I should be smart about this. I really shouldn't write out 1/2 times u times the square root of u squared minus 25 minus 25 times the natural log of u minus the square root of u squared minus 25. I should actually plug in what I've chosen for u, so I don't have to write out this terrible thing twice. So I'm going to say this is going to be 1/2, or I guess I should start with 1/3 times 1/2 times parentheses u, which is x cubed, times the square root of u squared, so x cubed squared, minus 5 squared, minus 5 squared, times the natural log of the absolute value of u, which is x cubed, minus the square root of u squared, which is x to the sixth, minus a squared, which is 25. Save yourself a little bit of grief and don't write it out all with u's and then go back in and plug in what you know. Right? If you know you're gonna have to plug back in what u is equal to, you can save yourself a step there. And sometimes it's worth it. Some, like here, I definitely think it's worth it. I don't want to write that out again. So that's kind of the long and the short of the using these integration tables. It'll probably be a little bit harder than what we've done in that you're gonna have to, you're probably not gonna be told, oh, use this formula. They might like narrow it down and say like your formula's in this section, but then you have to decide which formula you're actually using. Okay. So it sounds like we haven't talked about partial fractions yet in class, but it's kind of the next thing, so we should. I can't imagine it's not going to get talked about. It's pretty standard topic. I often refer to partial fractions as a method of last resort, meaning you should make sure you've tried other stuff before you try partial fractions. For example, let's talk about partial fractions. Although this first example is actually not going to be partial fractions. So here's my first example. It's going to be x plus 3 over x squared plus 6x plus 8. I will point out that this integral meets all of the criteria to use partial fractions. The criteria being you have to be integrating a rational function. The 1, the integrand, which is just the thing we're integrating. The integrand is a rational function, meaning polynomial divided by another polynomial. No square roots, no trig functions, no e to the x's, no natural logs. All you can have are nice non-negative integer powers of x on top and non-negative integer powers of x on the bottom. If you have any other weird, funky negative powers or fractional powers, no dice. Quick aside, sometimes you might start off with something that looks heinous, and you might do a u sub and then get something where you can actually use partial fractions. That does happen occasionally. Second thing that has to be true, the degree on the top has to be strictly less than the degree on the bottom. The degree on top here is 1, the degree on the bottom here is 2, we're good to go. Thirdly, we must be able to factor the denominator as much as possible. But at least, I say as much as possible, but it also has to factor at least a little bit. Like if it doesn't factor at all, if you're stuck with something that's unfactorable, you can't use partial fractions. It has to factor at least a tiny bit. And then if it does, you factor it as much as you can. And then before you do any of these things, you should double check you couldn't have done something else first. So looking at this, it definitely meets all the criteria. Rational, degree on top is smaller than the degree on the bottom, and the bottom does factor as x plus 4 times x plus 2. And before I thought of any of that, I should have checked to make sure that I couldn't have done a u substitution first. And I totally could. I could do a u sub. So check for a u sub first. It won't usually work, but here it does. If I let u equal the denominator, x squared plus 6x plus 8, my du is going to be 2x plus 6 dx. And then dividing both sides by 2, 1/2 du is equal to x plus 3 dx. And I exactly have that. Oh, there's something in the chat. Let's take a look. When you say slightly fewer for the degree, so what I mean is that the degree on top, which is the highest power of x, has to be strictly smaller than the degree on the bottom, which is the highest power of x. So in this case, the degree on top is 1 because the highest power of x is 1. The degree on the bottom is 2 because the highest power of x there is 2. So the degree on top is strictly smaller than the degree on the bottom. It can't be less than or equal to. It has to be strictly less than. And we'll see an example later on where the degrees are equal to each other, and we have to do something else before we can do partial fractions. So now this one, though, not partial fractions at all. We would just rewrite this as the integral of, well, let's say I have a 1/2 du on top, I have a u on the bottom. If you really like, you could write it as 1/2 the integral of 1 over u du. I think you can skip that and just say that you have 1/2 natural log of the absolute value of u plus c, which is then 1/2 the natural log of the absolute value of x squared plus 6x plus 8. Let's see. So make sure before you start throwing partial fractions at a problem to at least check to see if you could have done something else. Usually u sub is the only thing that was really an option if something else is an option. Okay, but now let's look at something that's very similar, but not at all similar in how we're going to do it. We're going to look at the integral now of, sure, let's say 2x plus 5 over x squared plus 6x plus 8. And, if it was just a little bit bigger, if it was 2x plus 6, we could again totally do a u substitution. But we can't. It's not going to work out if we try it, so let's move on. And let's try partial fractions. So for partial fractions, after we've identified that all the criteria are met, then you're going to take your expression and you're going to factor the bottom. So we're going to write this as 2x plus 5 over x plus 4 times x plus 2. And then completely outside of the integral, we're going to do some algebra. So we're going to rewrite this expression, 2x plus 5 divided by x plus 4 times x plus 2. And we're going to write it as the sum of some fractions. We're going to write it as some unknown constant divided by x plus 4 plus some unknown constant divided by x plus 2. Basically, you're breaking up this fraction. It's kind of like if I said, you have the fraction. Let me think here for a second. Let me make sure I pick something that's not silly. Sorry, let me do some quick math over here. 1 second. Times 3 times 7. It'd be like saying, let's say you wanted to write the fraction 13 over 21, but you wanted to write it as the sum of fractions with simpler denominators. You could say, oh, that's going to be some a over 7 plus b over 3, because 21 factors as 7 times 3. And then you can multiply both sides by 21, and say 13 equals 21 times a over 7 plus 21 times b over 3. And then 21 times a over 7, the 7s cancel, and you get, you don't need to write this part down, by the way. This is probably just kind of demonstrating. You can, though. 21 equals 3 times a, and 21 times a over 7 is 3 times a. 21 times b over 3 is 7 times b. And then you could try to find numbers that kind of made this work. The process for actually finding them is a little bit more straightforward. Here, I'm just going to tell you one possible answer would be that a is 2 and b is 1. So that 2 times 3 is 6, 1 times 7 is 7, and 6 plus 7 is 13. So you can totally write this as 2/7 plus 1/3. So the idea here is to take a more complicated fraction with a more complicated denominator and write it as the sum of fractions with less complicated denominators that are still factors of that more complicated denominator. That's the kind of idea that we're espousing here. So, looking here, the next step in the process is I don't want to deal with fractions. So we're going to multiply both sides by the common denominator. So we're going to take this expression, 2x plus 5 over x plus 4 times x plus 2 equal to a over x plus 4 plus b over x plus 2. And we're going to multiply both sides of this by our common denominator, which is x plus 4 times x plus 2. Okay, here's what always happens. On the left-hand side, the denominators will always completely cancel, and you'll just be left with whatever the numerator was. In this case, 2x plus 5. On the right-hand side, we have to be a little bit more careful. But the point of doing this, the point of multiplying by a common denominator ever, is that you're getting rid of all the denominators. When we simplify this expression, we should be left with things that are no longer fractions. So when we distribute the x plus 4 times x plus 2 to the a over x plus 4, the x plus 4s cancel. And we're left with a times x plus 2. And then when we distribute that to the second term, the x plus 2s cancel. And we're left with b times x plus 4. All right, I'm going to show you 2 ways to solve this because there's a better way, and then there's a way your teacher's probably going to show you, which is the less easy way, in my opinion. But you still be aware that they produce the same result. So here's the thing I think you should always do when you're solving partial fractions constants. We're going to pick the convenient values of x. This equation is true no matter what x is equal to. It's true if x is 0, it's true if x is 1, it's true if x is 1,000. I'm going to pick values of x that make something go away. So let me ask both of you. Those of you on campus as well. I'm on Zoom as well. What value of x could I pick so that this term was no longer there? What would x need to be so that the a was gone? -2. So we can do that. Let's do it. We're going to pick x equal to -2, and then we're going to plug it in for every x. So we're going to get 2 times -2 plus 5 equal to, I don't even really want to write it, but I will write a times -2 plus 2. But we should just know that that's going to be 0 and not even write it. Plus b times -2 plus 4. And then simplifying, on the left-hand side, I have -4 plus 5, which is 1. On the right-hand side, I have a times 0, which is 0, plus b times -2 plus 4 is 2. And then solving for b, I get 1 divided by 2 is equal to b. Great. Why don't you all do the same thing and pick the other convenient value of x? I don't want to tell you what it is. I'm pretty sure you can figure it out. Pick that convenient value of x and solve for a. And when you're done, let me know. You should also get a fraction for a. Hopefully x equals -4 was the choice you both made, and people on Zoom as well. And if you plug that in, I'm going to show a little bit less work this time. I'm going to say I've got -8 plus 5 equal to a times -4 plus 2 plus 0. And then -8 plus 5 is -3 divided by -2 is my a value. So I'm going to get a equal to +3/2. This is the way I would always do it. Now, one caveat is that if you have a more complicated situation, which we'll talk about a little bit, sometimes you'll run out of convenient values, which is unfortunate, but it's true. And then you kind of have to, what I would say is that doesn't mean you shouldn't use them. You should still use them. And then after you run out, you should pivot to this other thing we do, which is typically called equating coefficients. So we could have totally solved the system in a different way, which I'm going to show you right now, because I do want you to see it so that when your teacher talks about it, like, oh, that's what they're doing, because they'll probably talk about that. So the other way to look at this is to, let's just go up over here. We're going to say, all right, I'm going to multiply this out. So on the left-hand side, I have 2x plus 5. On the right-hand side, if I actually distribute the a and the b, I have a times x plus 2a plus b times x plus 4b. Now I'm going to group the terms together. I feel like there's a nicer way of saying that other than grouping terms. I'm collecting terms. So I have 2x plus 5 on the left. And I have on the right a plus b times x. And then 2a plus 4b. Which I don't really need to put parentheses around, but I am going to anyway. So look here for a second. These two polynomials are equal to each other, which means the coefficients have to all match up. So it has to be true that 2 is equal to a plus b. We need for sure that a plus b is equal to 2. It also has to be true that 2a plus 4b is equal to 5. And then you can solve this system of two equations and two unknowns in whatever way you like. I personally like elimination, but a lot of people like substitution, where I could say, all right, I'm going to take this. Now I'm going to do elimination. I'm going to multiply this equation by -2. So I'm going to have -2a minus 2b equal to -4. I just multiply by -2. And then if I add those together, what's 2a plus -2a? 0. And then 4b plus -2b is going to be 2b. And then 5 plus -4 is 1. And then divide by 2. Oh, look, you get b equal to 1/2. And then you could either eliminate the other way, or you could just say, if I take this first equation here, if I plug that back in, then a plus 1/2 equals 2. So a equals 2 minus 1/2, which is 3/2. You get the same values either way you do it. To me, it certainly seemed like the first way we did it was easier, which I hope you agree with. But if you don't, but also if you don't agree, if you think this is otherwise easier, then do it that way. You are not bound to doing it one way or the other. unless your teacher says you have to do it well, it feels silly. But we do this. So again, I'm gonna say whenever we're faced with something that is more or something else like this, we're gonna start with this, and then if we run out of values, then we're gonna pivot to that. We'll talk about that in some other examples here. We're not done. We found the partial fraction decomposition, but we still actually wanted to do an integral here. So then we're gonna go back and say, oh, what this means is that now we can say, can we say? Maybe. We can say that since our 2x plus 5 over x plus 4 times x plus 2 is equal to a over x plus 4, so that's going to be 3/2 over x plus 4 plus b over x plus 2. Now we can do the integral. We can say, great. Then the integral of 2x plus 5 over x plus 4 times x plus 2 dx is equal to the integral of 3/2 over x plus 4 plus 1/2 over x plus 2. I think it's perfectly fine to integrate this straight away if you can see how to do it. But if you feel like you need to massage it a little bit here, get other pens. There we go. We could break this apart as 3/2 times the integral of 1 over x plus 4 dx plus 1/2 times the integral of 1 over x plus 2. I think you can skip that personally and just jump straight to saying 3/2 times the natural log of the absolute value of x plus 4 plus 1/2 times the natural log of the absolute value of x plus 2. Let's see. That's what you get. Questions about this example before we hit some more examples? Okay. So yeah, let's look at another. Yeah, we got time. So let's look at this next example. Did I remember that one? I didn't. Let's say we want to integrate. Sure. 3x plus 1 over x cubed minus 5x squared minus 6x. Sometimes the algebra or the arithmetic gets pretty messy on these, so be diligent. I would point out, I don't even need to think about a u sub here, so I let u equal to the denominator. The du is definitely not going to be the same as the top because I'm going to have an x squared in my du, and I don't have an x squared on top. So skip the u sub. Hopefully the bottom factors. Let's see if we can factor that. So looking at a partial fraction decomposition, x cubed minus 5x squared minus 6x, I can rewrite as x times x squared minus 5x minus 6. Technically, you factored it, but you have to factor it as much as you possibly can. So factoring that further, x squared minus 5x minus 6 does factor as x minus 6 times x plus 1. So now we're ready to say, great. 3x plus 1 over x times x minus 6 times x plus 1 is equal to a over x plus b over x minus 6 plus c over x plus 1. You're just taking each factor and writing constant over that factor plus constant over the next factor plus constant over the next factor. Cool. So then multiply both sides by the common denominator. Here's what I like to do when I do this. I like to put just one big parentheses around the whole equation and say, we're going to multiply that whole equation by x times x minus 6 times x plus 1. So when we multiply it over here, the denominators completely cancel, and you're left with just 3x plus 1. You don't have to show this work, like you can kind of jump to the next step, but I think it's good to show this work because it's kind of like how when you're doing a u sub, and you get really, really used to just being like, okay, you said du is equal to this, but what you're really doing is you're taking the derivative of your choice for u and then multiplying it by dx. It's good to remember where the thing what you're doing, what you're doing came from. It's good to remember where the thing came from. You're really multiplying both sides by this, and then you're getting, on the right-hand side, a times everything except for x. So x minus 6 times x plus 1 plus b times everything except for x minus 6. So x times x plus 1 plus c times everything except for x plus 1. So x times x minus 6. That's what's going to happen when you distribute this to each of those other terms. And now we get to play the game of picking nice values of x. Okay, I'm going to call on your names. Victoria. What's one nice value of x I could pick here? Perfect. Cassie, what's another one? Positive one is not one of them, actually. So the question I'm really asking, although I'm not saying it that way, is what value of x could I pick that's going to make some of these factors equal to 0? Right, exactly. And finally, what's the last one? Which is less easy to see, I feel like. The last one is 0. Because if I put, right, this x by itself is really like an x minus 0. So these are my 3 nice values of x. And so we're just going to plug them in. So if I plug in x equal to -1, be careful here. We do have to plug it in on the left-hand side. Sometimes on the left-hand side, there'll just be a constant there, so there'll be nowhere to plug it in. But if there is an x, we need to plug it in. So on the left-hand side, I'm going to get -3 plus 1. On the right-hand side, watch for a second. I'm going to get a times something times 0 plus b times something times 0 plus c times -1 times -1 minus 6. You really only need to write the term that isn't going to be 0. And then we have -2 on the left equal to c times -1 times -7 is 7c. So c is equal to -2/7. Same deal here. If I plug in x equal to 6, I'm going to get 3 times 6 plus 1 on the right. So 18 plus 1 equal to a times 0 plus b times 6 times 6 plus 1 plus c times 6 times 0. And then I'm going to get 19 on the left equal to 6 times 7 is 42. So that's 42 times b, which is going to give me b equal to 19 over 42. And then finally, plugging in 0 for x. On the left-hand side, I get 0 plus 1. On the right-hand side, I get a times -6 times 1. Plus b times 0 times 1 plus c times 0 times -6. So solving for a, I end up getting 1 divided by -6 is equal to a. Or a is equal to -1/6. And then we can totally go back and rewrite the integral. We can say, great, the integral, in fact, we can even just do it on the same piece of paper here. We plugging in these values and using this kind of expression here, we're going to have this is equal to the integral of a over x, so -1/6 over x, plus b over x minus 6, and 19 over 42 for x minus 6, plus -2/7 c over x plus 1. And then we do the integral. The integral usually, I know those numbers look kind of awful. They're really almost not, they're almost not even there. Because really, let me show you what I would write, and let me show you the intermediate step that I'm not going to write. I would take this integral, -1/6 x over x, plus 19 over 42 over x minus 6, plus -2/7 over x plus 1. And be like, okay, well, I'm ignoring the -1/6 or whatever constant. I'm just pretending like there's a 1 up there. The integral of 1 over x is the natural log of the opposite value of x. So I'm going to get -1/6 times the natural log of the opposite value of x. And then the integral of 1 over x minus 6 is the natural log of the opposite value of x minus 6. So I'm going to get 19 over 42 times the natural log of the opposite value of x minus 6. And then the integral of 1 over x plus 1 is the natural log of the absolute value of x plus 1. So I'm going to get minus 2/7 times the natural log of the absolute value of x plus 1. Let's see. You can, if you want or need to, break this up into 3 integrals and bring out the constants, right? As -1/6 integral of 1 over x plus 19/42 integral of 1 over x minus 6 minus 2/7 integral of 1 over x plus 1. But I really, really, really don't think you need to do that unless you want to. Okay. So, yeah, we got time. All right. So something else to be aware of here is, well, in fact, yeah, let's look at an example here. So I'm not going to do this next integral. I just want to know, how would I set up the partial fraction decomposition for, let's say, f of x equal to, let me see here. Sure. X cubed plus 2x plus 1 over, let me think for a second here. Yeah, fine. I gotta be careful. Sorry, I'm trying not to do that. Sorry, 1 second. It takes me a minute here. Oh my gosh. Sorry. Brain fart. Sure. Over x to the 4th plus x cubed minus 4x squared minus 4x. So I want to set up the partial fraction decomposition for that. And the first thing I have to do before I can set up the partial fraction decomposition is I have to build a factor of the denominator, which looks kind of tricky. So what can I for sure factor out of the denominator? X. So I'm going to rewrite x to the 4th plus x cubed minus 4x squared minus 4x as x times x cubed plus x squared minus 4x minus 4. But then what about the rest of this? Well, there is kind of a tricky thing happening here, which is that we can factor the rest of this using factoring by grouping. If you have an even number of terms, 4 in this case, you might try factoring by grouping if nothing else seems obvious. What factoring by grouping is you look at each pair of terms. Looking at the first pair, x cubed plus x squared, what's the biggest thing I can factor out from x cubed plus x squared? Right, and you're left with x plus 1. And then the hope is that you can factor out something from the next pair that leaves behind the same thing. Here, I can factor out a -4, which still leaves behind an x plus 1. And then I can factor out the x plus 1 from each of those pieces and get x times x plus 1 and be left with x squared minus 4. And then finally, the x squared minus 4 factors as the difference of squares. So you're going to get x times x plus 1 times x minus 2 times x plus 2. Which means we could then set up our partial fraction decomposition as x cubed plus 2x plus 1 over x times x plus 1 times x minus 2 times x plus 2. And it would just be equal to a over x plus b over x plus 1 plus c over x minus 2 plus d over x plus 2. And that's all there is to setting it up. Right? They didn't say solve it. They just said set up the partial fraction decomposition. Okay. The reason why I'm emphasizing this is because as long as each factor is raised to the first power, you got no issues. Everything's just nice and what you would expect to see. But if someone says something like set up the partial fraction decomposition, which I'm just going to write out as set up the PFD, the partial fraction decomposition, for the following, it's going to be a little bit more interesting. Let's say we have, I'm not going to factor it, yeah. 2x squared plus 5x plus 1 over, let's not make it too terrible, x cubed times x plus 1 to the 4th power times x plus 2. Okay. Here is what happens when you have repeated linear factors. So I'll point out that in this first one up here, I had 4 linear factors. I had x to the first, I had x plus 1 to the first, I had x minus 2 to the first, and I had x plus 2 to the first. And each of those linear factors corresponded to one of those things there. And I had 4 pieces in my partial fraction decomposition because I had 4 factors. So now the number of pieces I'm going to have isn't going to be 3. So I don't just have 3 factors. I have 1 factor repeated 3 times, 1 factor repeated 4 times, and another factor repeated once. So my partial fraction decomposition is actually going to have 8 pieces. 3 plus 4 plus 1. And here's what they're going to look like. And this is where it gets kind of terrible. No one would ever ask you to like actually solve this one, but they could ask you to set it up. So here's the setup. Do I have enough room? Yeah, I have enough room. You're going to have a over your first linear factor raised to its highest power. So a over x cubed. And then you need more terms with every lesser power of that linear factor down to 1. So I need a b over x squared plus a c over x. All right, I'm done with x. Now I move on to x plus 1. I have a d over x plus 1 to the 4th, and then every lesser power. So I have e over x plus 1 cubed plus f over x plus 1 squared plus g over x plus 1 to the 1st. And finally, I have an h over x plus 2. And that would be the partial fraction decomposition for this terrible thing. So the point here is that when you have a repeated linear factor, x plus or minus some constant, the constant could be 0, raised to some power that's higher than 1. So 2, 3, 4, right? It has to be an integer power. Then you have to do this sort of thing. So let's look at an example of something you might actually integrate using this process. Let's say we want to find the integral of 3x minus 8 over x cubed minus 4x squared. Yes. Again, not a u substitution, right? If I let u equal the denominator, the du is not going to be a nice multiple at the top. So we move on, we start thinking, well, can I factor the denominator? And I can. I have 3x minus 8 on top, and the denominator factors as x squared times x minus 4. And it's fully factored. Are those birds I'm hearing? Oh, it's a desk. Because I was like, I don't think it's like I feel like it's coming from Cassie, but I was like, but it's not like what you're writing with. I was like, I thought it might have been like someone behind me in another room writing with the squeaky. Okay, not a big deal. I was just like, I was really like, where is it? So then the partial fraction decomposition, 3x minus 8 over x squared times x minus 4. People, I feel like, get confused about x squared. They're like, that's not linear, James. It's quadratic. It's raised to the same power, but it's really a linear factor repeated. I'll just point out that x squared is really x minus 0 quantity squared. It is a linear factor that is repeated. Some x plus or minus a constant raised to a higher power. So then when we start writing this partial fraction decomposition, I'm going to have a divided by x squared, and then every lesser power of x down to 1, which is going to be b over x. And then plus c over x minus 4. And then we do the usual thing. We multiply both sides by the common denominator. It's red pens thing again. So we distribute, and just like always, when you distribute over here to the thing on the left, you always end up with just the numerator because it's exactly the denominator that you're multiplying by. So we need 3x minus 8 on the left, and then we distribute to these terms here. A over x squared times x squared times x minus 4, the x squareds cancel, and you get a times x minus 4. Multiplying by b over x, only one of the x's cancels, and you get b times x minus 4. And finally, multiplying it by c over x minus 4, the x minus 4's cancel, and you get c times x squared. When you have repeated linear factors, like in this example, we are going to run out of convenient values of x. It's just always going to happen that way. That doesn't mean we shouldn't use them. They're still very useful. So my convenient values of x here are x equal to 4 to make that part 0, or x equal to 0. So let's start with x equal to 0 because that's easier. So plugging x equal to 0, on the left-hand side I have 3 times 0 minus 8. On the right-hand side I have a times 0 minus 4 plus 0 plus 0, which we shouldn't write down. So let's see, I end up getting negative 8 equal to negative 4 times a. So a is equal to negative 8 divided by negative 4, which is positive 2. Great. Lovely. Now let's use x equal to 4. Plugging in 4, on the left-hand side I have 3 times 4 minus 8. On the right-hand side I have a times 0 plus b times 4 times 0 plus c times 4 squared. You don't need to write the ones where you have a 0 as a factor. They're just going to be 0. So let's see, I have 12 minus 8, which is 4, equal to, sorry, I'm just looking at something here. Okay, yeah, that's fine. Equal to 16 times c. So c is 4 divided by 16, or 1/4. Okay, we have run out. There are no more nice values of x. Even here at this juncture, you have a choice. So in a choice, kind of depend, the goodness of your choice depends on how much there's left to find. If there's exactly one constant left to find, which there is in this case, you could make the choice to pick another value of x. So one option here would be to say, I'm gonna pick a nice easy number of x for x like 1. And if I plug, I might actually pick 2. So I could pick x equal to 2, and then plug in my values I found. So watch for a second. If I do that, I'm gonna have 3 times 2 minus 8 on the left equal to a, oh, but I know what a is, so let's plug it in. So equal to 2 times 2 minus 4. I don't know what b is yet. Plus, I'm gonna run out of room here. b times 2 minus 4. Plus, I do know what c is, 1/4 times 2 squared. By the way, that's why I picked 2 instead of 1. Because I knew that if I picked 2, 2 squared would be 4, and 4 times 1/4 would be an integer. Just to make my life have less fractions in it. Now I can solve for b. So let's see, 6 minus 8 is negative 2, equals 2 times negative 2, plus b times 2 times negative 2 is going to be b times negative 4. And then 1/4 times 4 is 1. Adding the 4, subtracting the 1, so negative 2 plus 4 is 2, minus 1 is 1. So 1 is equal to negative 4b, so negative 1/4 is equal to b. And this is probably about as nice as it actually gets if you choose this route. It can be a lot less nice if you have grosser fractions here. So I would usually not recommend doing it this way. The other option is to say, equate some coefficients. Typically, you would start off with the highest power of x you have. So if you look at this equation here, what's the highest power of x we have on either side? Is it x squared? Is it x cubed? Is it x to the first? Is it x to the 0th? Which one is the highest power we have? X squared. So then we're going to look at how much x squared we have on either side. Okay, it's going to sound kind of like a silly question, but how much x squared do we have on the left side of this equation? None. So on the left-hand side, you have 0x squared. On the right-hand side, I don't have, so looking at my terms, if I multiply this out, I would have a times x and a times negative 4. I'd have b times x, which is b times x squared. Oh, I have a b times x squared. And I would also have a c times x squared. Or in other words, 0 has to equal b plus c. But then, since I know that c is equal to 1/4, I can say that negative c is equal to b, or negative 1/4 has to equal b, which is what we got that way. That's the way I would choose to do it. So if I was doing these partial fractions problems, I would always first exhaust all of my convenient values of x equals 0, x equals 4. And then when I run out of those, then start equating coefficients of x to figure out what the remaining constants are. That's the best way I have found to do it over the years. Finally, now we get to integrate this thing, right? So, right, it's always feels kind of like you kind of are like, oh, we did all the things. Like, no, we didn't. We found all the constants, and then you have to go back and actually do the integral. So then we're going to go back and we're going to plug into our integral, and we say, okay, the integral of 3x minus 8 over x squared times x minus 4 is going to be the integral of a over x squared plus b over x, which is minus 1/4 over x, plus c, which is positive 1/4 over x minus 4. Now be careful. We've gotten into the kind of habit of seeing most of these being logarithms when you integrate them. That's not going to be true for this first piece. The integral of 2 over x squared is not 2 times the natural log of x squared. You should be thinking of this part here as 2x to the negative 2. And when you integrate it, you're just going to use the reverse power rule. So you're going to end up getting 2x to the negative 1 divided by negative 1 minus the rest of these will be logarithms. 1/4 natural log of the opposite value of x plus 1/4 natural log of the opposite value of x minus 4. Let's see. And not that I would simplify this, but just to point out a common simplification that you might see. So let me show you something real quick here. I would rewrite this as negative 2 over x. And then here you might see someone do something like this. You might write this next part as 1/4 times the natural log of the opposite value of x minus 4 minus the natural log of the opposite value of x. And then you might see them combine those logarithms as they still have negative 2 over x plus 1/4 times the natural log of the opposite value of x minus 4 divided by x. I'm not saying you need to do that. In fact, I'm explicitly saying you probably don't need to do that. But you might be looking at the answer in the textbook and seeing this instead of that. And this is what they've done. They've just combined it to make it look nicer and take up less room. So that's a fine answer, but really I would just leave it like this. I probably wouldn't. I'd probably simplify this first part to be perfectly honest, but it wouldn't mess with the logarithms there. So that's what happens if you have a repeated linear factor, is you have to do this adjusting. Let's look at one more example, because that's all we have time for. Not that one, though. I don't want to do that one. I want to do not that one either. Do we not have one of those? We could do that one. That one's lame, though. Sure, we'll do that one. Okay. So maybe two examples. Let's say we have the integral of x squared minus 4 over x squared minus 1. Does the bottom factor? Can you factor x squared minus 1? For sure. X minus 1. It's certainly rational. Is the degree on top less than the degree on the bottom? Absolutely not. So before we can do anything, if the degree on top is bigger than or equal to the degree on the bottom, then before you can do any sort of partial fraction shenanigans, we have to do polynomial division. So we're going to do x squared minus 4 divided by x squared minus 1. And it's a pretty easy polynomial division. It's one step. X squared times 1 will give you x squared. So then 1 times x squared minus 1 is x squared minus 1. And we subtract. And you get x squared minus x squared, which is 0. And negative 4 plus 1, which is negative 3. What this allows us to do is then rewrite our integral as the integral of the quotient 1 plus the remainder divided by the divisor. Negative 3 divided by x squared minus 1. And then, if you really wanted to, you could break it up and say it's the integral of 1 dx, which is just x, minus the integral of 3 over x squared minus 1 dx. And then for this part here, this is where we're going to use partial fractions. Because now it's a rational function where the degree on top is less than the degree on the bottom, and the bottom still factors. So we'll come back to this, but let's do the partial fractions thing. So we're going to have 3 over x squared minus 1 does factor as x minus 1 times x plus 1. And we're going to set that equal to a over x minus 1 plus b over x plus 1. It doesn't matter which order you put these in, right? I could have done x plus 1 first and x minus 1 second. It literally doesn't matter, as long as you just are consistent. And then we're going to multiply both sides by our common denominator. So we're going to get multiplied by x minus 1 times x plus 1. So we're going to end up with 3 on the left equal to a times x plus 1 plus b times x minus 1. What are my two convenient values of x? I know you know them. One of them would be x equal to -1. The other one is x equal to +1. Plugging in -1. Oh, look, there's nowhere to plug in x on the left-hand side, so I just get 3. On the right-hand side, I have a times -1 plus 1, which is 0, plus b times -1 minus 1, which is b times -2. So -3/2 is equal to b. Similarly, plugging in x equal to 1, I get 3 on the left equal to a times 1 plus 1. So 3 plus b times 0. So 3 divided by 2 is equal to a. Cool. So then we can rewrite this whole thing as, that's right, I've lost room here, so I guess I'll go up. This is equal to the integral of 1, which is x, minus the integral of a over x minus 1 plus b, which is going to be -3/2 over x plus 1. Sorry, I've kind of written this in the worst orientation possible here. And then integrating this, we're going to get x minus 3/2 times the natural log of the absolute value of x minus 1. And minus and minus will be plus 3/2 times the natural log of the absolute value of x plus 1. Let's see. So polynomial division first is required if your degree on top is larger than or equal to your degree on the bottom. And sorry, I wrote things in kind of the worst order possible, but it did, so sorry. Guess we have time for one more. Oh yeah, we'll do, yeah, we have time for one more. One more fun one. So let's look at this integral. The integral of x cubed divided by x squared minus 4. Again, we have a situation where we have to use polynomial division because the degree on top is larger than the degree on the bottom. So let's see what we get. So I have x cubed. So typically when you have a higher power on top, sometimes it makes sense to write out, oh my gosh, to write out the division the right way, maybe. Sorry, 1 second here. Got it again, James. So I'm going to have x cubed divided by x squared minus 4. And sometimes, depending on how comfortable you are with the polynomial division, you might want to write out all the missing terms. It's like 0x squared plus 0x plus 0. You surely don't have to, but it is sometimes easier. Here, it's actually not really necessary because if you multiply, well, what do you multiply by x squared to get x cubed? Just x. And x times x squared is x cubed, and x times -4 is -4x. I'm going to put it beneath the 0x here. But then when I subtract, I get x cubed minus x cubed, which is 0. 0x squared minus 0x squared is 0x squared. And then finally 0x minus 4x is plus 4x. And now this 4x here has a lesser degree than our divisor, so we stop. We can't continue the division. It's kind of like when your remainder is too small, right? You don't continue to, well, I mean, you do if you want the decimal expansion, but here we just stop. So we're going to rewrite our expression x cubed over x squared minus 4 as the quotient plus the remainder divided by the divisor. And this is where it'd be really easy to do too much work. Because you might at this point be like, oh, we did partial, or we did polynomial division, so then we're going to do partial fractions. And often that's right. But here, we shouldn't get fooled because instead of doing partial fractions, we could do a u substitution. So I'm going to rewrite this as the integral of x plus the integral of 4x over x squared minus 4. And then I'm going to point out that this one here totally works if we do a u sub. You could also do partial fractions though. You shouldn't. If you can do a u sub, that is the thing you should do. You shouldn't do partial fractions. But here, if we let u equal x squared minus 4, du is going to be 2x dx. I'm going to go a different direction slightly and say that 2 times du is equal to 4x dx. And then rewrite this as the integral of x, which is x squared over 2, plus the integral of 4x dx becomes 2u du. The denominator is 2u du, James? Is that really what I have on top? What do I really have on top? 4x dx is equal to not 2u du, just 2 du. I accidentally put in an extra u there because I wasn't paying super close attention. Just be a 2 on top and a u on the bottom. And then the integral of 2 over u is 2 natural log of the absolute value of u. And then finally plugging back in what u is equal to, we get x squared over 2 plus 2 natural log of the absolute value of x squared minus 4 plus c. So after you do polynomial division, often partial fractions will be the way to go, but occasionally someone will do something sneaky and make it so that the fraction you're left with is u subbable.